Hello and welcome back to session 3 of NACAA 2022. My name is Stuart Beveridge and I am the NACAA 2022 convener and chairperson for the day. Next on the agenda will be How to Get Started in Astronomy by Perry Vlahos. Bitten by the astronomy bug in his very first science lesson at secondary school, Perry Vlahos is an astronomy educator, author and broadcaster. Perry is a long-term member of the ASV and has previously been president on a number of occasions. So Perry, you have the floor.
Thank you, Stuart, and good afternoon, everybody. Thanks for joining us, and I hope you've not had too many eggs to make you feel sick. How to get started in astronomy. I hope, first of all, you've not confused astronomy with astrology, because you would be at the wrong presentation if you have. Mind you, when as a younger man, I dated an astrologer, and I've told this story before. We used to take romantic walks in the night, balmy nights of summer, and holding hands. And one night she said, Perry, look, the moon is in Pisces. It means it's a wonderful night for making love. And I looked up with my astronomical bent, and I could see the moon was nowhere near Pisces, but I knew when to keep my mouth shut. So let's move on, and my mouth is going to be flapping for the next half hour or thereabouts. This is a personal perspective because I've pretty much made all the mistakes that it's possible to make in astronomy. I've looked through just about every type of telescope. I've fallen into pitfalls, misunderstood many things. So hopefully I can give you some tips to avoid the mistakes that I've made. And I fully understand that some people may have a different perspective to me as to how to go about this. But I think this works. It's worked with me. It's worked with other people. So in order to increase our knowledge, and it is what we want to do, we all want to peek behind the veil and see what there is in astronomy and how we can be part of it, a little bit like this pilgrim from, I think it's a Camille Flammarion book from the 1800s, this woodcut. So we need to peer and see how we can get started. Well, the most obvious way, and it's a no-brainer really, is to join an astronomical association. Now, I'm a member of the ASV and a member of other associations, and the ASV is the largest one in Victoria. In fact, it's the largest one in the Southern Hemisphere, and it's full of people with great knowledge. They're all friendly and very happy to help out. So go to the website, to the ASV website, and have a look around. There's other societies as well. There's Mount Burnett, a wonderful organisation, a little bit out of Melbourne, up in the Dandenong Ranges, but if you're near them, try them out. If you're heading south along the peninsula, or if you're in that area, maybe you can try the Mornington Peninsula Astronomical Society. But any of them really, because they will all be too glad to help you get started and take your first steps. Now, I'm a cheapskate. I don't like spending money, and I wouldn't advise any of you to spend a lot of money to get into astronomy in the beginning. And of course, astronomy is the cheapest thing to get into because it costs nothing to just look up. And you can do that, but also take advantage of other free offerings from associations like the ASV. Go to their monthly meetings. They're free. Anyone can attend. You can ask questions of people there, and it helps you along the road. You can go to some of their public viewing events. This one is the Messier Star Party up at the Dark Sky site, but there's also events around town, and it gives you an opportunity to see in situ how other people go about it. One of the other things that you can do is read, and I cannot stress this enough. I've put up the website here of Australian Sky and Telescope magazine. It's a wonderful publication. You can buy it in a newsagent if you still do that sort of thing, or you can go online and have a look at it. There's a multitude of great astronomical websites all over the place, but read as much as you can so that you're gathering knowledge as you go along. Then there's books. One of my favorites is this one, but there are heaps of others as well that you can buy. Or if you join the ASV, for example, and I'm sure it's the same with the other societies, whatever city or state that you're in, you can borrow books from their library, generally for free, and you can do that with the ASV. Once you get into it a little bit more, you may want to try something like this publication here. Here's the Sky and Telescope magazine, by the way. And if you get more serious, here's the star atlas that I would recommend. However, you can get lots of apps for your phone and online and whatever. But there is one thing to avoid, and that is don't have it too dark, because it makes your pupils close down. And then, sorry, did I say too dark? What I meant was don't have it too bright, because bright white light will make your pupils close down. And when you look back up at the sky, you're not going to see all the fainter objects that may be much more interesting than just the brightest stars. Again, being a cheapskate as I am, and I hope you don't want to spend too much money in the beginning either, as I said earlier, go to this website, which is skymaps.com, run by a gentleman I'm proud to say is a friend of mine from Adelaide, Kim Felicides. And this sky map is one of the best maps I've ever seen anywhere on the internet, and you can download it for free. It comes in 2 pages. This is the chart page, but also there's a second page that gives you a lot more information about the objects that are displayed therein. But I will need to give you a few little tips on how to get the most out of this chart. One of the things that you're going to need is this thing, or I'm holding one here live in person, and it's a red light torch, which only throws red light onto a white chart. Red light least affects our eyes and doesn't destroy our dark adaptation. So that's what astronomers use, and you can get all sorts of red light torches. You can spend tens of dollars or even hundreds of dollars if you want to spend it on this one, because it also has a number of other functions, including a green laser pointer, which I use in my talks, or a cheaper one might be something like this. But once again, ladies and gentlemen, don't spend any money if you don't have to, and until you're very, let's say, committed to it and you want to get better at this particular hobby. But what I did originally is got one of these, and it's just a regular torch, and I got some red wrapping paper and just put it over the business end with a rubber band to hold it into place. And that works just as well. Red paper finished off with a layer of cellophane, or just red paper on its own, is just as good. But let's go back to this. Now, one of the things that many magazines and also books, and I've even seen live demonstrations of this, tell you to do when you want to use a chart like this, is to hold it above your head and look up at it that way. Don't do that. Here's why. You will need this, and you will also need the chart. But look what happens when you hold it up. So you're holding the chart up above your head, and then you want to shine the light on it. Watch what's going to happen. As Julius Sumner Miller used to say, why is it so? Well, it's gravity. So don't do that, because the paper will not stay up. And this is 160 weight paper as well. So thinner paper is not going to help. Here's what to do. Hold it up just like you may be reading a book, but never look beyond halfway on the chart. If you want to look beyond halfway, turn the chart over and face the direction that's at the bottom of the chart. That way, it's much easier to just look and compare. So the other thing you will see around the outside of the chart, it has the directions. Down here, it's south, east, west, north, whatever it is. So whatever direction you are facing, you've got to turn the chart so that that direction is at the bottom of the chart. So if you're looking, north, turn the chart so that north is at the bottom. A good little giveaway is that the writing on it is the right way up. If it's not the right way up, you're not holding it the right, with the correct direction and the correct orientation of the paper. The other thing to look out for is on the side here, it tells you which times, month, and whatever this chart is valid for. And when you do go to the website, make sure you do download a chart of the southern hemisphere, not the northern hemisphere, or the equatorial hemisphere, well, not hemisphere, but the equatorial chart of the sky. So if you're in the southern hemisphere, please make it the southern hemisphere chart. The other thing along the bottom here is, if maybe we should go back to the other chart here, you can see that there's star magnitudes, and there's a big one, a smaller one, continuing to get smaller until we get to this one, which is about as faint as what's contained on the chart. So the bigger stars are obviously the ones that are going to be the brightest and easiest to see in the sky. Sirius, Canopus, Alpha Centauri here, Beta Centauri. The first three are the brightest stars in the sky, as distinct from planets, however, because Jupiter, Venus, and Mars on occasions can be brighter than these stars. The other tip I'm going to give you is don't wait until it gets really dark. Start observing maybe half an hour after the sun goes down. The reason for that is because then only the brightest stars are visible. None of the fainter ones are visible, and so they'll not confuse you. So find these bright ones first, Sirius again, Rigel, Betelgeuse, all of the bright ones to begin with, and then start looking for the fainter ones as it gets darker. But hopefully by then you would have had a good grounding on finding the main ones. This band through the middle of the sky, at the moment at least, because its position does change, is the Milky Way. However, don't expect to see it if you're observing from the inner city or the suburbs of a large city. You will only see it to any satisfaction from rural areas away from city lights, because lights, well, let me go back a step. We all know that the natural enemy of the mouse is the cat, and the natural enemy of the cat is the vacuum cleaner, or, according to my vet the other week, the thermometer. Think about it. But the natural enemy of the astronomer is the electric lamp. So you've got to get away from lights as much as possible and find a spot, whether it be in your yard or whatever, or a long way from the city if you want to get that serious, so that you can see the sky as it was intended. Now, let's move on. So the next thing you want to buy is what? A telescope? No, don't buy a telescope yet. Now, some groups will let you borrow a telescope, a lone scope, so that's something to explore. But what I suggest you get first of all is, as that's myself and Steve Roberts here, we're looking at Comet Hyakutake back in 2007, and Steve's got my binoculars. So that is what you should begin with next. Get some cheap ones, because everybody wants to get binoculars. You don't have to just use them for the sky. You can watch your missile launch, watch the races, go to the beach with them, the football, as I am tomorrow. So they're easy to use and go anywhere, but you want to aim them up so that you can have a good look at the stars and the sky with them as well. But please don't spend more than about, I don't know, if you spend more than $150, you're spending too much. And in the early stages as an observer, you probably won't be able to tell the difference between binoculars that are $100 or $150 and binoculars that are $1,000. So get the cheap ones first. And what to avoid is any binoculars that have strong tinting over the front of them, because usually they're hiding imperfections of the lenses. The lenses might even be plastic, which are to be avoided. So avoid that. Don't buy binoculars that are way too big as well, because they're heavy and difficult to hold up. So avoid those. Here's what I use. These are also waterproof. I think they come in under $150. And you can use them anywhere, and they're quite cheap. Before you buy a telescope, go somewhere where an event that an astronomical association is running, where you can look through some telescopes, see what other people are using. This is an event I run every year for our members. It's learning how to use your telescope. And I even allow people to come to the event so that they can see, even if they don't have telescopes, that they can have a look and see what other people are using and find out more before they buy a telescope. Because there's nothing worse than somebody coming up to me at one of these learn to use your scope sessions and saying, here's my scope, I got it for $39 from Aldi or something. And then it's just too late to give them any good advice. So get all the advice before you go and splurge money. Some of the telescopes to avoid. Not this one. Doesn't even have a finder scope. A bit too small to show anything with satisfaction. Same with this. Yep, another one to avoid. Notice there's no finder scope up here. Even this one, despite it having a finder scope, it's not what I would recommend. If you've already got one of these, well, use it. Get as much out of it as you possibly can. Here's another example of something similar. These are reflectors because there's a mirror down at the bottom here and another mirror that pushes the view out to there, to the eyepiece where you observe from. So, hang on a moment. It's not moving. Now let's go the other way. And again, don't buy this one either. Even though it's got setting circles here and other things, they don't really work very well. And even this one, despite it being in Dick Smith's recommendation, or does he still own National Geographic? Maybe not. It's just a little bit small. If you've got one, well, use it. Try and get the most out of it. This is what I would recommend and what the ASV has recommended for many years. It's a Saxon branded telescope, and we don't mind giving them a bit of a plug because they've assisted us in the past. but really it can be any brand of Dobsonian 8-inch telescope. And the truth, well, I'm not sure if it's the truth, but I suspect, and others have said the same thing to me, that all of these brands' telescopes are now made in the same factory in China, and they just put little different finishing touches on them. But they're all pretty good, whatever brand you want to get, but make sure it's an 8-inch and it's a Dobsonian. It's a reflector, and you could probably use this for many years before you run out of objects to look with it. How much would you spend for a scope like this? Well, relax, it's not thousands of dollars. I believe they come in at under $700, which is a bargain. And watching Sarah speaking about the golden age of astronomy this morning, I would also like to say that the golden age of astronomy is right now, because never have telescopes been as cheap and never have we had as much knowledge to access about astronomy. Oh, here's mine, and I'm standing here on top of the ABC, but I want to point out this little doohickey here, which is another tip. It's called a telrad, and my telescope has not had a finder scope on it since I bought it over 30 years ago. And I've been able to use it to see incredibly faint objects without a finder scope. But without this telrad, I would have been lost in space, as Dr. Smith would say. How does it work? Well, it fits over the top of the tube of your telescope, and it gives you a bit of a heads-up display like you would get in modern fighter jets. So you look through it, and this is what you see: concentric circles with your target in the middle. So a little bit like a bullseye. Some people have difficulty with it because of one thing: they close the other eye. I'm here to tell you, ladies and gentlemen, that it's not easy to use this if you close your other eye. The trick to using this telrad successfully is to keep both eyes open, one on the real sky, one through the telrad. And that way the two mix in your brain and you get a really good idea of what you're looking at. Nothing is upside down. You don't have to do mental contortions. Now, some of the things to avoid. Sorry, that's my timer. Damn. I'll finish up. Some other things to avoid: cigarettes. Now, why? Because cigarette smoke has a detrimental effect on not only the optics of telescopes, and it begins the corrosive process on them, but also it constricts the blood vessels in your body, including your eye. That previous picture was a bit too glamorous. Think of cigarettes like this and you're more likely to avoid them. Also, avoid alcohol for the same reasons. They constrict the blood vessels in your eyes and you don't see the faintest objects as well. So even though cheers and slurp might taste pretty good, try and avoid them when you're observing. Sunglasses, well, you know, why shades? Well, because you want to be able to look as cool as these guys. But not only that, what they do is they preserve your night vision during daytime hours. So some people go to the extremes of covering their telescope eye with a patch during the bright sunny afternoon so that it's not... so it's more ready to see the faintest objects because it's not being exposed to bright light. Now, finally, some of my favourite chocolate, because if you're trying to observe a faint galaxy of 14th magnitude or a 13th magnitude planetary nebula, and you've tried every trick, including tapping the side of the tube to get movement, because our eyes notice movement much more readily, then break out the safety chocolate and have a little bit of lint or whatever you've got, because that surge of blood sugar makes your eyes perform a little bit better. Thank you very much for your attention, ladies and gentlemen, and enjoy the rest of NACAA.
Thanks, Perry. There's I've got a question here.
Sure.
From Sergio Marinzek in Brazil. Perry, Sergio from Brazil, normally magnitude 6 is considered norm, but for us that live close to the city, that's impossible. Any tips on how to look for good objects lower than that?
Yes, I'm glad you brought it up, Sergio, and extremely correct in saying that from the city, it's very difficult to see past about 4th magnitude. And to see the faintest objects, it's good if you can get away out to the country. If you can't get to a park, if you're in Melbourne, I don't know what there is in South America, and I'm not sure how good your access is to the Amazon rainforest or the Andes mountains, which would be ideal, but try and get to a local park. Here, we sometimes go to Wattle Park to observe. Near where I live, Cheltenham, there's a good park there. Just get away from lights as much as you can and go through some of the lists that give you deep sky objects that are brighter than 6th magnitude. Say things like the Pleiades, for example, they're visible from the suburbs, and also sometimes, depending on the conditions, the Eta Carinae Nebula and Omega Centauri may also be visible. But yes, it is a problem, and there's no easy way to get around the lights of the city, except perhaps to try and talk our local councils into putting shielding around the lights.
Another question now, Perry, from Charlie Boston. Is there a way to take a picture of the moon when you don't have the special camera attachment?
Well, yes, there is, Charlie. Good question. My first pictures of the moon were just taken with my phone up against the eyepiece, but you can get a fairly cheap attachment for holding the phone to the eyepiece, and then you can get better results. I think the attachments cost maybe $10 or $15. You can find them on the internet, maybe even eBay. And then you can get some pretty good pictures. The opening picture that had the moon in it in this talk when I began was a picture I took with this phone through my telescope. So you can get pretty good results without special camera attachments. And again, as a cheapskate, I managed to get away with only spending about $15 on it. Any more, Stuart?
I think that's just about it, Perry, but I think it's very important. I remember when I started in astronomy, I was lying out one warm night, unable to sleep, and I thought, looking at the sky, I might go and buy a telescope tomorrow from Kmart, and you can work out how bad that ended up. And then from there, I progressed slowly through a whole lot of telescopes that were totally unsuitable before I then joined the ASV and found out a lot more about what it was I should have done right from the start.
It is a journey, Stuart, and you're right. Most of us have all made these mistakes because we just didn't know any better. That's why it's important to read, to explore on the net, to seek out local astronomical associations and get their advice, because there's a lot of knowledge out there and people are happy to give it to you for free. Did Sergio want to ask another question before we go?
Just there's another one here. Yeah, he hasn't put one in yet though, but we might be able to squeeze it in. From Ian Enting, how do you navigate the trade-off between aperture versus portability to get to darker skies?
Yes, a very important question. An 8-inch f4.5 or f5 or even f6 telescope is maybe, about 60 inches or thereabout. That's the tube. That will fit in most cars. It won't fit in my 2-seater sports car, but I do have a second beaten up old Mazda with a lift back that it fits into the back of. And we used to be able to get 2 telescopes into that and drive to the country. But yes, it is a balancing act, Ian, and I think check out how much room you've got in your car. If it doesn't fit in the boot, some cars, the boot opens up and you can put things through the back seats, or it can lie on the back seat or on the floor. So you're just going to have to suck it and see, as the classic saying is.
And just to finish off, Perry, there is one more from Sergio. Can solar flares disturb our way of life regarding electronics? A large one we've never had.
We have had some large ones, and again, another good question, Sergio. Electronics is not my speciality, but I do remember in the 90s, I believe, that electricity grids went offline in Canada and in the US. New York and I believe Los Angeles were plunged into darkness, and everyone was totally afraid of it, except for the astronomers. They grabbed their telescopes and went out to observe. So one man's Playboy is another man's pornography, as they say. So I don't know whether it can knock out electronics like computers at the telescope or whatever, but certainly power grids have been knocked out in the past.
Thank you very much, Perry. I'm afraid we're going to have to leave it there. That was a great talk, and you had a lot of really positive comments coming in, and thank you very much.
Thank you, Stuart.
Our next presentation is entitled Using Gravity to Find Stars by Peter Osmond. Peter is a member of the Sydney City Skywatchers and Astronomical Society of New South Wales. Peter is a physicist, engineer, and has been interested in amateur astronomy for 10 years. You've got the floor now, Peter.
Thank you. I'm presenting this as a video because it will contain some demonstrations that could only be carried out by video. So hopefully everything will go well. Thank you for the opportunity to describe this project. It started some years ago when I was learning how to record spectra from fast eclipsing binaries, and the stars I was interested in required consecutive days of measurement. But the clouds in Sydney make this difficult. So I resolved to put together an instrument that could be taken on a bus or train to clear dark sky campsites well away from Sydney for a few days of measurement. Trouble was, I couldn't find an equatorial go-to mount that could point to a star with an accuracy of 1 or 2 arc minutes, that could be carried by hand on buses and trains and along a kilometre or 2 of dirt road, and which had the battery capacity for a week of measurements. This talk is about how I solved the issue, and in particular, how I found a way to point a telescope at a star accurately using gravity. The talk will cover the basic principles, how to build the gravity reference star finder on the kitchen table, demonstrations of the system operation, strengths and weaknesses, and finally, a few star finding examples. So, portable astronomy. On the left-hand side of the slide, there's a photograph that is essentially the vision for this project. There's an instrument box on a trolley that holds the telescope, cameras, equatorial mount, counterweight, and sometimes a spectroscope or other equipment needed. On my shoulder is a tripod, and that can be either a Benro or EQ3. They're both reasonably robust. And I'm carrying a backpack with enough supplies for a long weekend. The right-hand side shows details of the implementation. The EQ3 is my preferred tripod, being a useful compromise between rigidity and portability. It's connected via an adapter plate to the Star Explorer, which was about the smallest equatorial mount adequate for the task, and the mount connected to a Takahashi 60mm refractor, which I selected not just for its optical qualities, but also because it's very robust. The imaging train was a flip mirror with eyepiece and either a Matic 314L or ZWO 120mm camera. There are also 2 unconventional pieces of equipment, 2 black boxes, one underneath the red dot finder and another mounted beneath the declination plate. And these hold the declination and hour angle accelerometers that allow me to point at stars to within 1 or 2 arc minutes. Before going much further, it's worth looking at the advantages and disadvantages of using gravity-referenced accelerometers versus star alignment using optical encoders. One key difference is accuracy. Optical encoders are accurate to arc seconds, whereas accelerometers of the kind I'm using on small telescopes are accurate to 1 or 2 arc minutes. So, if you're looking at fields of view much less than half a degree square, or you're guiding your telescope, then optical encoders win hands down. However, the other key difference is stability of your baseline reference. Gravity is extraordinarily stable, and clouds don't bother it, and a gravity reference telescope can be calibrated during the day in your study, and once calibrated, generally only needs to be leveled and pointed south when you're on site. Whereas the alignment of portable telescopes with optical encoders is weather dependent and likely needs to be done at night in the dark every time you set the gear up. Other issues are that fitting optical encoders to a telescope that doesn't have them requires significant instrument making skills. I mean, I really don't want to be drilling holes in my Takahashi. Whereas accelerometers can be fitted using industrial grade 3M stickers, and in this case, knowing a bit of trigonometry does make fitting them easier. High school trigonometry, that is. Another benefit is that setting up an accelerometer system on your scope will highlight defects such as cone error and allow you to correct them. And finally, it's really hard to find an accurate go-to telescope that can be carried along with its imaging equipment by hand across several kilometers. So the niche for this technique is likely to be amateur astronomers who live in city apartments under cloudy, light-polluted skies, who would like the opportunity to use a small telescope for science projects rather than imaging. And I think it also has a place in people who want to recycle equipment or to restore antique telescopes. I should explain how an accelerometer works. So first, the basic principle. Imagine two metal plates, one heavy and hanging by stiff springs from the lighter one that you're holding. Then as you rotate that assembly, going from right to left, from a position with the lighter one on top to a position with the heavier one on top, the distance between the plates decreases. Now, it's possible to measure that rotation electronically. It's effectively an electrical capacitor that's increasing as the springs compress. And it's possible to measure that rotation by using an equation that relates the decrease in the distance between the plates, in other words, the increase in the capacitance, to the amount of rotation. And the accelerometers and silicon chips are constructed as a microscopic version of this assembly. So here's a typical single chip microcontroller, an electronic board, and the chip might be just one of the chips on this board. And here's a schematic of what that chip looks like. It has two springs, one here and one here, and the plates that are moving backwards and forwards are represented by the black plates and the grey plates. The black plates are being moved with respect to the grey plates. And that's how an accelerometer is constructed on a chip that you put on an electrical board such as this. It's about 0.5 millimeter in length. And that's the principle. That's one of the contributors to measuring how your telephone rotates when you turn it. This slide shows two electronic boards fitted to my hole-free Takahashi. One of the boards is used for declination and the other for hour angle. Each board has 3 accelerometers to measure rotations around 3 axes, but only 2 of the 3 accelerometer axes are needed to find the declination, rotations using the X and the Z axes, and only 2 are needed to find the hour angle, rotations using the X and Y axes. The unused rotation measurements aren't wasted. They can be used to measure the polar altitude difference between the telescope axis and the tracking motor axis, or for polar alignment. Now, you don't have to fit the accelerometers in this orientation. You can choose other orientations by swapping axes, so long as they're at 90 degrees to each other and to the hour angle or declination angle, i.e. orthogonal. If you find an alternative orientation is easier to implement for either sensor, there's a defined section in the accelerometer program that allows you to swap the axes without having to reprogram the mobile phone app. The equations that work out where to point the telescope are given here. There are the basic hour angle and declination equations, and a set of coordinate transforms that convert from the mathematical frame, where the mathematics is done, to a differential frame which controls the telescope, and then to a frame that displays the result according to astronomical conventions. It's worth noting the discontinuity at due north in the control system reference. That's because I'm in Australia and can hide the discontinuity where it won't have any effect. If I were in the northern hemisphere, the discontinuity would be due south. There have been several attempts to use accelerometers and gyroscopes as setting circles for equatorial mounts, but they appear to have been unsuccessful, except for a project by the Research Center for Astronomy and Earth Sciences in Budapest, and the project described here. Typical issues that plague such attempts are the dreadful drift and variability problems associated with semiconductor gyroscopes and magnetometers. I found that accelerometers are the only semiconductor sensors capable of measuring to arc-minute accuracy. Another issue is that there are a few different math solutions for hour angle and declination. And while they may work on a massive, stable, and precisely engineered telescope, but everything goes to pot when you transfer them to a typical amateur telescope with relatively inaccurate machining tolerances. For example, both my original declination expression and the Budapest hour angle expression were unstable when used on an imperfect mount. So I've taken the best of both worlds and used the stable Budapest declination experiment at my version of a stable hour angle equation as shown above. And I used differential measurements between a reference star and target star as one would in star hopping. Now, the issues I referred to in the previous slides were related to unstable equations that returned impossible numbers in response to machining inaccuracies. So, for example, the purple and blue indicated values of greater than 1 for the sine or cosine of hour angles at 0, or plus or minus 6 hours. Or in the declination case, we have two green regions where the equations required a division by 0. So that was the problem, but fortunately there was a combination of equations from the Budapest Institute and my own work that gave two stable equations that could get rid of those problems. Well, the maths might be awkward, but assembling the system is not. It's possible to put it together on a kitchen table in a couple of hours just using hand tools. The electronics can be purchased off the shelf, as can all the necessary connectors, and there happens to be commercial plastic boxes that are close to ideal for holding the electronics. There's no machining required other than to hand file a slot for the connector in one edge of the box. The electronics is held in place using a soft 3M Scotch mounting tape to create support pads which also dissipate vibration. And best of all, the box can be mounted on or peeled off the telescope equipment using industrial-grade 3M extreme fasteners. The photograph shows command fasteners, but I've recently found that extreme fasteners are more stable. The trick with the fasteners is to cut them into 3 pieces and place them with the centerpiece at right angles to the other 2 pieces, so that the grain in the fasteners runs in 2 directions. This stops the box from rocking along a grain line. I placed the power bank outside these boxes because batteries can interfere with the magnetometer. And while I complained earlier about the magnetometer, it may be useful for finding magnetic south in places that you visit frequently, so long as you don't place a battery too close to it and calibrate it for your location. This is to demonstrate a mobile phone app that can be used to align your telescope, calibrate it, or point it to a target star. I've cast the screen of the mobile phone to the left-hand side of the computer screen as a mirror image. And you can see at the top of the screen a number of parameters, which the hour angle and the declination are the most significant for this project. But as well as that, we have the altitude and the polar altitude, which can be useful in improving the alignment of the telescope, and likewise the azimuth and the magnetic south, which can sometimes be useful when setting up in the field. In the bottom half of the screen are the control buttons, and on the bottom right, we have a scan button, which switches on the Bluetooth channels. The A channel is used for the declination, and the B channel is used for the hour angle. Once they're connected, you can start the calculations by pressing run. And the values will take a little while to stabilize because we're using quite a strong filter to suppress vibration, mechanical vibration noise and artifact. And that has a delay associated with it. And now we've got it running, just demonstrate by moving the telescope to axes how it operates. We're moving it through the hour angle axis, like 6 hours approximately. back up to 0 hours to +6 hours. Again, approximately, a bit of a stretch. There you go. Likewise, I can adjust the declination control, set the declination values between 90 degrees plus or minus 30 degrees. I won't take it all the way, just to conserve time. Set button is used to point the telescope. So when I press it, it highlights the declination, and the value showing can be 0 by moving the telescope through the declination axis. And that's done. Press it again, and I can 0 the hour angle. Again, shows a value can be 0 by moving the telescope through the hour angle. When that's done, the telescope should be pointing at the target star. Another important button is the calibration button. When I press that, it prompts the user to place the telescope in a particular position. Now, I'm just going to put it in the horizontal position to take a demonstration. And when it's positioned, press the set button, and that will store all the measurements from each of the axes of both the accelerometers. And we do this 15 steps, each step representing a different position. Once all those 15 steps have been carried out, the computer can calculate calibration factors for each of the accelerometer axes, both the declination and the hour angle. I'll just take it through those steps now, because having started to finish, I'm not going to see the prompts changing as I go. I'm not going to place the telescope in different positions, just again to conserve time. Normally, this would take half an hour, but that's only has to be done once. Unless, of course, you have changed the configuration of the mount. That's finished. Now, once the calibration has been finished, you should be able to point the telescope in a few arc minutes. However, you can, if you wish, optimize the calibration further by looking at the individual accelerometer axes values. To do that, there's always the IMU data list at the bottom, where you have the declination axes values, which are the A values, and the hour angle accelerometer values. So you might be interested in optimizing one or two of these axes, focus on those, make those measurements at particular positions, and go to the calibration list on a page. And these, again, are all changeable in real time, and you would adjust them according to the values that you have measured in the data list. Now, that does require a certain amount of trigonometric knowledge, high school trigonometry, but it's not essential. It's just a means of refining the calibration, best accuracy possible. Another screen that's useful is the single star offset screen. Let's go to star offsets again. So in this screen, you can set the coordinates for any single star. For example, APSO might be calling for volunteers to carry out observations on a star, and they would give them the hour angle and declination. You can put this into the target hour angle, target inclination here. Then you get a suitable reference star and with its coordinates, a reference hour angle, a reference declination here. Press the offsets button to calculate the offset. You can see they're 0 because, of course, I haven't entered any data. But whatever data I had entered and whatever offsets were generated can be transferred to the main screen for immediate use. And they can also be stored as a record in the data. So here they are, 0, of course, in the data. There were, similarly with the hour angle, 0 data, but if there were 0. And once you've done that, pointing at the star that ASO had asked. Now, I did just mention the database, so I go to that. The database can manage 120,000 stars. Of course, you're not likely to measure all of those. It does give you good choice. And the main purpose of the database is to be able to set up drop-down lists of the most regularly used stars. Typically, that would be a drop-down list of about 100 stars. I'll just show you. If I wanted to select a target star from the drop-down list, open it up, go to the Puppis, for example, which is a star I'm interested in, and it's now a target star. Likewise, you might want to select a reference star, and there's no best reference star to get the Puppis is Rigor. Let's select that. Again, that's now got coordinates for both the target star and the reference star. So pressing the offset button, those offsets, which I can now transfer to the main screen, and they're ready for use. I can 0 the declination offset, I can 0 the hour angle offset, and I'll be pointing at the up. And that's the end of this slide. Thank you. We've seen the software in action, and I did promise that I'd talk about the software development and what was needed to install it. If a project like this is to be widely accessible, there's no point in using programming languages that require months of intense training. So for the mobile phone app, I've selected an educational language called App Inventor. It was developed by MIT for students, and it's very simple to use, and it's superbly well documented and supported by the developers in the community. Likewise, the accelerometer code uses Arduino, which is essentially the programming language C, and again, that's well documented and supported. The links to each are given here for the MIT App Inventor, and here for the Arduino code, and they take you to the introductory pages. Having said that, there's really no need to know how to program. All that's necessary is to compile the App Inventor mobile phone app and the Arduino Accelerometer code. The reason the code hasn't been compiled is that there's now so much malware around that accepting APK or exe files from strangers is hardly wise. Compiling the Push2 mobile phone app and the Arduino Accelerometer app is very easy. Just import the phone app, press build, and download it to your phone using Google Drive. Likewise, with the Arduino software, just connect the accelerometer board to the computer USB board, paste in a text file, and follow the Arduino instructions. The compilation process for both of them is usually just a minute or two. I mentioned earlier that the only area that requires the user to adjust the code is if you want to change the orientation of the accelerometers. The required change is highlighted in yellow here. Working out the equations, although they're very simple, does require a bit of high school math, or I could provide a table in the manual of the equations needed for different orientations if there's enough interest. Now, on to the next video. This is going to show the zeroing process that points the telescope. You won't see the telescope move much because the star hop being demonstrated is quite small to save time. There'll also be short periods when I'm quiet while focusing on adjusting down to a minute or two of arc, so don't adjust your set. Keep an eye on the declination and hour angle displays. This will show the strengths and weaknesses of the system. On one hand, the numerical feedback to the operator allows a declination adjustment to a minute or two of arc, but this is despite the coarse gear train and vibrations created because there's no mechanical isolation of the control rod from the telescope, so it requires practice. The hour angle, on the other hand, can be motorized, and it has a finer gear train and reduced vibration, as it is mostly hands-off. So it'll achieve the offset zero quite smoothly. However, the use of a strong filter to reduce vibration does mean the operator still has to take account of a time delay. I think there's a lot of room for improvement in this part of the task, and the potential to make the process faster and smoother, but I have to do a bit of thinking about that. Now, this is a short demonstration of how to point a telescope to a star using gravity-referenced accelerometers as setting circles. The first step is to select a reference star that is visible and close to the target. The next step is to point your telescope at it, and that's what we've done here hypothetically. And then we move to an app on a mobile phone which controls the accelerometers. And we look up coordinates for the reference and the target stars on the database on the mobile phone. First, the reference star, which is Delta Crucis, and then the target star, which is Epsilon Crucis. Having got the coordinates, we calculate the offsets, and we transfer the offsets to the main screen, and it's ready. Now, 2.2 star. Do this by pressing the set button, which tells us we have an offset 1 degree and 39 minutes. Explanation. This has to be reduced to 1 or 2 arc minutes by rotating action control. Short adjustments. A period of rest in between each adjustment. It allows a rather strong filter to take out artifacts due to mechanical vibration. It's inevitable whenever it's a push-through system. And then getting down to 1 or 2 Moving on to the hour angle, this can be reduced by using the tracking motor, running at 12 times speed. That's what we'll be doing now. And if it were many degrees, I would use the counterweight to rotate the telescope roughly and finish off with the tracking motor. I won't have time to do that on a short demonstration. While it's doing this, it's also compensating for the Earth's rotation. When we get down to about 1 minute, take account of the filter, switch it off, and it will drop it down to 0.2 a minute, or roughly that. There you are. We'll now be pointing at target star. Thank you. I'll now show you a few star pointing examples. And this first slide is an example of working backwards and forwards between Alpha and Beta Centauri, each taking it in turn to be a target and a reference. This is a stock method I use when trialing new modifications. The table on the left is worth explaining. The error value is the actual distance in arc minutes between the star and where it should be at the center of the crosshairs. The distances are the hour angle and declination offsets between the two stars. The apparent accuracy is the error as a percentage of the total distance, and the theoretical accuracy is the 2 arc-minute accuracy limit of the technique as a percentage of that distance between the reference and target stars. It assumes that the telescope is perfectly machined and aligned, so that it is ultimately determined from the 16-bit resolution of the analog to digital converters. In this instance, the apparent accuracy is better than the theoretical accuracy, but that's most likely just luck. On this slide, the error at 3.6 arc minutes is more realistic, being slightly greater than the theoretical 2 arc minute limit. And this is an example of working blind, that is, finding an invisible object. It was one of the first invisible objects that I was able to find using this technique. Here is another example where the actual target star has been colored red to determine the error. And again, this is very close to the theoretical limit. I was inspired to find this star by a comment Alan Plummer made in Sky and Telescope, where he wrote of BY Sculptoris that it's a tough find using star hopping. That was because it's a cataclysmic variable and its magnitude can vary intermittently, so you can never be sure that it will be visible. Alan was kind enough to validate my position for BY Sculptoris. These images were taken in my backyard in Sydney. The telescope was a 60mm Takahashi FC60. The mount was a Star Adventurer. The camera was a ZWO ASI 120 mono. And the image is made by stacking 5 by 30-second exposures. It is stretched and with a cutoff to remove sky glow, and I've used dark subtraction to remove camera hot pixels. The preliminary calibration and setup took 7 minutes to find true south. And then to find a star, it took 1 or 2 minutes to push the telescope from Fomalhaut to BY Sculptoris. The last time the system was calibrated was about 4 weeks prior to the measurement. I also made a note at the time of the difference between the declination value as measured and as given by the Carp-to-CL catalogue. And this demonstrated that while the absolute measurement of the gravity reference system gives values in the right ballpark, the error is still sufficient to require the differential measurements be used. Well, as you can see, there's still quite a bit of work that could be done. While it's by no means a commercial system, it might nevertheless be of interest to people living in small apartments in cloud-covered, light-polluted cities, or to anyone wanting to recycle a telescope, or add go-to capability to an antique telescope. And if any of you are interested in this system and have questions, please don't hesitate to send a note to ultralightscopes@gmail.com. In conclusion, I found the project a fascinating exercise, and it taught me a great deal. And rather oddly, despite its idiosyncrasies, it's now my preferred method for finding stars, largely because it doesn't involve massive cables and computers. I can easily read the display in the dark, and most of the work can be done during the day, so the precious dark time is not wasted. It's also a bit of a drawcard at public demonstrations, where people seem attracted to its simplicity. I guess that there's some truth in the saying that the best telescope is the one you use most. Thank you for listening, and the Sydney City Skywatchers, the Astronomical Society of New South Wales, and the NACAA for all their encouragement.
So now, if anyone does have any questions, I'll endeavour to answer them.
Yeah, thank you for that, Peter.
I have to say I spent most of the, I went down sick quite seriously for about a year. And that's what gave me the opportunity to develop the software and refine it. Otherwise, I would never have had the time. So it's an ill wind.
Peter, there's a question from David O'Driscoll. Are you using this for imaging or other types of astronomical work?
No, it's really not it's not an imaging system. For a start, an EQ3 is hardly the mount for doing serious imaging. It's intended to be used for scientific work, not the highly sophisticated scientific work that has been described, but work that a relative newcomer like myself could perhaps contribute to. And its main purpose is to be able to travel to dark skies. And I think anyone who's lived in Sydney for the last 2 or 3 months will appreciate why that's worth doing.
Question from Neville Fraser. Is the Arduino coding complex for this project?
No, the coding's not complex. Converting the string of data to a compact string and then transmitting it to the Bluetooth reliably was the most complicated part of it. The other part of complexity is not so much the coding, but the filtering. As you'll appreciate, you'll probably have noticed that when I was adjusting the telescope, it was quite jittery for the preliminary adjustments, and it stabilized the closer I got to the target. And that's because I've got an adaptive filter in there. That's a two-pole adaptive filter. It's fairly crude, and I think there's a lot of room for improvement there. So I'd say the filter is probably where the greatest complexity, the opportunity for complexity is. The actual data being transmitted is pushing mobile phones to their limit, and Massachusetts Institute of Technology didn't think it would be possible. And the first time I tried it, the phone greatly overheated. But not needing a hand warmer at the time, I worked and worked on it, and now it's quite cool.
Okay.
In fact, I'm not a programmer, so none of the coding was really that complicated.
Also in the Arduino world, there's a library, isn't there, that you can use of like subroutines.
Didn't use any of those.
Yeah. Okay.
I wrote in fact, the only libraries I used were for storing data, because the data storage, and of course, there's lots of subroutines available in the MIT App Inventor, and I had lots of help from them. And I wound up contributing the Bluetooth low energy algorithm that I used to their help board. I think probably more people have used that than will ever use the telescope.
And David Driscoll has said, seems like a useful technique for setting up a scope for doing some things like occultations.
That's very true. What I'm really interested in doing, there was some Chinese research that looked at VPuppis, did some spectroscopy on VPuppis, which is a binary, a fast binary, and they think that the orbit changed sufficiently to suggest the presence of a black hole in the vicinity, but they didn't prove it. And I thought there was an opportunity here to do some spectroscopy. And I was frustrated in that regard by clouds, because I have to do it over several weeks, or several days at any rate. But once you're in a dark sky, yes, I think its main virtue, this technique, is finding out errors in your, if you've got a cheap mount, finding out and correcting those errors. And the other principal virtue is being able to transport it on public transport, because I try not to use a car, and get it to dark skies.
Okay. Well, that looks like that's about it for the questions. So, Peter, thank you very much for that presentation. We appreciate you going to the trouble of doing that. And that concludes today's session 3. Session 4 will start at 3:30 this afternoon. Once again, if you go along to the NACAA website, you'll be able to have a look at the schedule for this afternoon. So with that, I will conclude today's session. Thank you very much, everyone.